Welcome to the Rust in Replit course. This course will introduce you to the Rust programming language. Within the description, there are links to various materials used and mentioned in this course. Specifically, there is a one-click link to the interactive course powered by Replit, which allows you to learn Rust completely within your browser. There is also a link to the slides mentioned, which can be used as a cheat sheet for Rust. Finally, there is a link to an article written by yours truly, which walks through Rust and the interactive projects. This course assumes intermediate knowledge in at least one other programming language. If you are new to programming, why not try the interactive freeCodeCamp curriculum? This is an interactive course going over the basics of the Rust programming language within your browser. First, you will get an overview of Rust. The course covers the basics of Rust, but you can also find some notes of this in the linked slides or article. Then, you can follow the interactive content to create your own CLI calculator, where you can perform basic arithmetic operations through the command line. Then, you will create an image combiner. This project takes two images and combines their pixels into one new image. First, an overview of Rust. A quote from the official Rust book. Rust deals with low-level details of memory management, data representation, and concurrency. The language is designed to guide you naturally towards reliable code that is efficient in terms of speed and memory usage. The main tooling within the Rust ecosystem are rustc, which is the compiler that takes your Rust code and compiles it into a binary, which is machine-readable code. rustup, which is the command line utility to install and update Rust. And Cargo, the Rust build system and package manager, which you'll get a lot of experience using throughout this course. And now, moving on to the first project, the CLI Calculator.
To begin, I have a REPL built using the Nix language in Replit. This allows me to define the necessary tooling for the project. A link to this template is available in the description of this video if you want to code along. You can use Cargo to create a new Rust project in the current working directory by typing in cargo new, followed by the project name, which we will call Calculator. This creates a new directory named Calculator, initializes it as a Git repository, and adds useful boilerplate for your project. The cargo.toml file is the manifest used by Cargo to manage your project's metadata. This is similar to a package.json file if you are familiar with those. The main.rs file is the default entry point for your application. You can see it contains a function declaration using the fn keyword with the handle main, as well as a call to the printline macro, which prints to the console. In Rust, a macro is denoted by the exclamation mark character, which is also known as the bang symbol. To run the project, navigate into the calculator directory. Then you can either use the cargo run command, which will compile your code and then run the compiled binary. As you can see, hello world is printed out. Or you can use rustc, which is the compiler, where you pass in an argument as the location to your entry point file. In our case, this is the source folder and the file is main.rs. This will compile your code into a binary, and it will be placed within your working directory. Then you can run the binary. Throughout this project, I will just be using Cargo to run the project, so let's remove that file. The Rust standard library comes with an env module, which allows access to the command line arguments passed when calling the program. The necessary exports from the env module for this project are the Args function and the Args struct. The Args function returns an instance of the Args struct and is imported into the file scope with the following syntax: use keyword, followed by standard, the module name env, the name of the function args, and the name of the struct args. To get an idea of what the args struct looks like, you can declare a new variable named args using the let keyword and assign the value of the return of calling the function args. Then, use the printline macro to print the value of the args variable. To do this, place curly brackets within the string as the first argument, and pass the variable you want to go within the curly brackets. Now, if you run this code, you will see the following error. Args cannot be formatted with the default formatter because the trait display is not implemented for args. That's a lot to take in. But for now, this error comes about because the printline macro does not know how to format the args struct. However, you can just follow the compiler's advice here to extend the formatter using the : syntax. Now, running this code, you should be able to see the output. As you can see, the args struct is printed to the console, and it contains an inner field which consists of the location of the compiled binary. You can confirm this by running the application and passing it an argument, freeCodeCamp. Now we can see freeCodeCamp is in the inner array. When we ran our code, you might have noticed that the compiler threw a warning saying we have an unused import. We don't strictly have to import args, but if you want to explicitly type the args variable, you can do so using the args struct that we imported, like so. Now running the code, that warning should no longer be there. To access the arguments within the args struct, within the args variable, you can use the nth method which exists on the args struct. First, let's declare a new variable named first, and assign it the value of calling the nth method on args. Hovering over the nth method, you can see the function definition, where it looks like it takes in 2 arguments. However, being a method on a struct, the first argument is implicit and is usually a reference to self, where self is the struct. In this case, this is a mutable reference to self. The argument that needs to be passed in is n, which is a usize, or a number. And it returns the nth element of the iterator, which is wrapped in an option. Let's unpack what all of that means. So, accessing the first argument by passing 0, it's printed to the console. You'll notice you will still get an error if you run the code. This error is saying that the args variable cannot be borrowed as mutable. We notice that in the definition, the nth method took a mutable reference to, in this case, args. So, in order to use the method, we need to declare args as a mutable variable. After doing that, we should be able to run the code. And this is what the first variable's value is. It is sum, wrapping the value we are interested in. Sum is a variant on the option enum. This will become more clear as we define enums later on. For now, just know that you can unwrap options to get the value inside. Rerunning this code, we should see that the value is no longer wrapped in sum. However, in this case, if we pass in an index where there is no argument, rerunning the code, you will see that the application panicked. Panicking is Rust's way of erroring out during runtime. You can see thread main panicked at called option unwrap on a none value. This is because when there is no value to access using the nth method, none is returned, as opposed to some with a value. So instead of unwrapping, let's just print that value. And first, the variable is none, and none has no value, therefore it cannot be unwrapped. To fix this, let's get the first argument out, and once again unwrap. Now running our code, you will see that we get freeCodeCamp. We know we want our application to take in 3 arguments, first being the first number, as well as an operator, being plus, times, divide, or minus, and this will be the next argument. Let's unwrap that, as well as a third argument being the second number. To get an idea of all of these, let's print them out to the console. First operator and second. Running this, let's add some arguments. We would expect to use this application by going 1 plus 2, for example. However, running this, our application panics. Apparently, we are still unwrapping on a none value. Well, which of these is the none value? Let's keep adding arguments to find out. The application still panics. 4. The application still panics. Now we are passing 6 arguments into the application and it is still panicking. Let's add more. Finally, the application doesn't panic. And this is because the nth method returns an element of an iterator, and we know it mutably iterates over the args variable. Internally, what this means is the nth method will look something like this, where we have a mutable reference to self, as well as n, which is the usize, or the index. And we know this returns an option, where it is either a string of the value we want, or none. Now south we know is our args struct, but what nth does is for each n, we can assume n in this case as an example. Assume it equals 0. So we are accessing the first element. There is some sort of iterator over self, accessing, let's say, that inner array, and it is calling next on that array. As you can see, next advances the iterator and returns the next value. So, in accessing the first element, when the nth method is called a second time, the iterator has passed the first element. So that second call, or calling next again, will result in the second element being passed. Let us look at it from this perspective. If at this point inner is equal to an array of these 2 arguments, calling next brings up the first argument. Calling next again would bring up the second argument. So as we are unwrapping here, and let's get rid of this. As we are unwrapping the variable into first, which in the case of our call would be 1, calling the nth method again on 2, this time starts at the plus argument, and 2 becomes the first element after that. And then 3 is the second index of the iterator. Practically, this means if we want to access the elements we are interested in, what we actually need to do when we are calling just this code, and we don't want it to panic, we want the first next element. Running this should yield what we want. Now, unlike some other languages, you cannot perform basic arithmetic operations on strings. And all of these variables that we have here are strings, so we need to parse them into numbers, or in our case, floats. So we can declare a new variable, first number, and set that equal to first, which is a string. Use the parse method on the string, which we can see here returns a result. And a result is similar to the option enum in that it can be unwrapped to get the value out. And we can do the same for the second number. It should be second.parse.unwrap. Now, we should get a warning that Rust doesn't know what type we want the number to be. Because there are many kinds of number in Rust, we need to give it a type annotation. And we can do this in many ways. One is to annotate the variable this way, in which case the parse method knows to take second as a string and parse it into an F32. Or my preferred method for doing this is to use something called turbofish syntax, which is fun to use and fun to say. This can be done because on the parse method you can see it accepts f, which is a type, and it returns a result of that type. So let's change second number to that as well. Now, let us declare a new function called operate. And this will take in the operator. And we can have the operator be a char, which is the type character. We will need the first number, which we know is an F32, and the same with the second number. Now we can use a bunch of if statements to compare if the operator is equal to the character we expect. For example, in this case, the addition character. And what we can do is return first number plus second number. Now, the first thing that we'll come across is an error. That there are mismatched types which expected an empty tuple but found an F32, and this is because we have not added a return type annotation to the function, and we can do that with this syntax. Another thing to note is the type char in Rust. This is a character literal made using single quotes, whereas if we had used double quotes, that would be of the type string. Let's continue with this logic. Add an else if statement comparing if operator is equal to the minus. Then we can return first number minus second number, else if operator is equal to divide by, then return first number divided by second number. And finally, the last operation we'll need is if operator is equal to an asterisk, or the multiplication operator. We will get a warning that we don't have all of our clauses, where the if statement is missing an else clause. This is because in Rust, if the operator did not match any of those, then the function will return an empty tuple. And as we have typed the function to return an F32, it cannot return an empty tuple. So we add the base case, otherwise return. For now, we can just return 0. But you'll notice you cannot just type 0, because it expects an F32, and floats require the decimal place. Something else to note about Rust is it allows implicit returns. What this means is you can get rid of the return keyword as well as the semicolon at the end. And this is exactly the same as what we had before, but this is the more Rustacean way of writing the code. And we can do this throughout. Now, to use the function operate, you can declare a new variable called result and call the function passing in the operator, first number, and second number. However, you'll notice that we get a warning because operator is of type string, but the function expects the type char. So we need to convert the operator into a character, and we can do this by using the chars method on the string, which returns an iterator over the characters of a string slice. And with the iterator, we can call the next method to access the first element of that slice. And the next method returns an option, which we know we can unwrap if the value exists. Now, we can print our result. Let's run the code to see if this all works as expected. And we can see 1 plus 2, the result is equal to 3. However, this is not the final output we want. And what we can do is declare a new function called output, which will accept the first number, which we know to be an F32, the operator, which is a char, the second number, which is also an F32, and then the result, which is that operation on the two numbers, which is an F32. We will want this to return a string, and in order to get the output the way we want, we can use the format macro, which is very similar to the printline macro, in that the first argument is a reference to a string slice. Which we can pass in additional arguments, which will be placed within the curly brackets. So we want first number, operator, second number, is equal to result. And format returns a string. Now, to use this, what we can do is call output and pass in first number, the operator, the second number, and the result. hopefully running the code gets us what we expect. And that's correct. 1 plus 2 is equal to 3. Let's try something else. Let's try 1 minus 2, negative 1. However, there's something much better we can do to improve the readability of the code, and that is instead of a bunch of else-if statements, we can use Rust's pattern matching expression, which starts with match, followed by the expression to be evaluated, which in our case is the operator, and then this is called a match arm, and what this is if the operator matches the plus character, then evaluate the following. First number plus second number. Now, because we are not including a semicolon at the end, this is implicitly returned, and we can continue with this logic. Now, we will get an error saying that we have a non-exhaustive pattern, because similarly to the if statements where we needed an else clause, the match expression needs a base case, which can be represented by the underscore, and we can still return the 0.0. And you will see that this code runs exactly the way it did before. However, returning 0 if the operator is invalid does not make too much sense. So it might make more sense to panic, and you can do that using the panic macro and pass it a message such as invalid operator used. Now what this will do is if an invalid operator is used, the code will panic. You can see it has panicked at invalid operator used. But now, what if we wanted to extend our application to not just accept multiplication? Oh, what's this error saying? This is an interesting case where we need to escape the asterisk in order to run the code. To get around that, you can extend the operate function to not just work with an asterisk, or not just match with an asterisk, which needs to be escaped each time, but it is common to multiply with an X. And we can extend it further using bitwise_or for a capital X. What this allows is instead of escaping the asterisk, we can just use X to represent multiplication. And now this will work just fine. And that is our application finished. All that's left to do is build it. And to do so, you can use cargo, build to compile the binary, and you can also pass the release flag. What this does is it provides some optimizations for the compiler and removes all debugging information. Running this will compile our code, and the code is found in the target directory, in the release directory, and it is called the binary's name. And we can run this code now with arguments. Oh, my bad. Add the period at the beginning. And there, we get the same result. So that is the CLI calculator finished. For the image combiner project, start by creating a new Rust project using the cargo new command, and let's call this combiner. Then cd into the combiner directory and run the project to ensure it is set up correctly. You should see hello world printed to the console. This project is bigger and more complex than the calculator project, so to prevent the main.rs file
from becoming too overwhelming, create a new file within the source directory called args.rs. This file will be a new module named Args, which will house the logic used to handle the command line arguments. Within args.rs, create a function named getNthArg, which takes a usize n and returns a string. Then we know from the previous project that we can access the env module inside the standard library and call the args function, chaining the nth method to get the nth argument. And let's unwrap the value. Now, to group the related command line argument data, you can create a struct named args. You've already encountered structs in the previous project. This was the string struct and the args struct from the env module. Instead of using the env args struct, you'll be defining a custom args struct specifically for use in this application. The string struct looks something like this, where we can declare the struct using the keyword struct, and it contains a Vec field, which is a Vec of U8s. Vec, in this case, is a dynamically sized array. So, following this syntax, create a struct named args with 3 fields. Image1, which is a string, image2, which is also a string, and output, which will also be a string. These will be the paths to the images passed as arguments. Within main.rs, the args struct can be imported once the args file is declared as a module using the mod keyword. So mod args declares the file as a module, and then we can import it using the use keyword. You can use the args struct by declaring a new variable named args in this case, and assigning it the value of the args followed by the field name and values for those fields. You will notice the error saying we cannot use args here because it is not public. It is a private field in a private struct. It is a private struct. To make it public, use the pub keyword before the struct definition. Now you will notice that each of the fields is also private. So similarly, before each definition, the pub keyword can be used to declare the field as public and therefore accessible outside of the current module. As you can see here, to create a new string, the new function has been used. The reason this function can be used is because it has specifically been implemented for the string struct. The implementation would look something like this. Where the function new has been declared
to be implemented on the string struct, where it returns self, being string, and as you can see, a string is created within it and implicitly returned. And the same goes for the new function within the Vecs struct. Now, if you are creating many Args structs, it would be beneficial to be able to do the same thing, that is, implement a new function on the Args struct within the Args module. So, you can use the impl keyword to implement new on the struct args, where new does not take in any arguments, and it will return self, where we can take that code we had previously here, this time returning it from the new function. Then we can call args new to instantiate a new arg. You'll notice that there is again an error that new is private. So before the function declaration, use the pub keyword to make the new function public. If we were to print out the value of args here, you'll notice two things. The first being that there is an error, which we've encountered before, saying that the trait display is not implemented for args. Now you may think that you could just extend this as we have done previously. However, we still get the error where the debug trait is not implemented for args. In order to implement the debug trait, we can actually follow the compiler's advice here to add this syntax to the struct definition. What this does, this is an attribute, it is deriving the debug trait for the Args struct. And after doing this, we should be able to print out the Args struct. However, you'll notice that currently the fields are all empty strings. This is not what is needed for the Args fields, so we can replace the string new call with the getNthArg function, passing in 1 as the argument to the first call, because the 0th argument is the path to the binary. Continuing this logic, we can pass in 2 to get the second argument, and similarly 3 to get the third argument. Now if we run our code, we should get an error because we are not passing in any arguments, so calling unwrap within the getNthArg function should cause a panic. What we can do is test this by calling our application with some arguments. And as we can see, image 1 has the value first, image 2 second, and output third. For this application, an external crate called the image is required to decode and encode the images. In much the same way other languages have libraries or packages, Rust has crates. You can add the image crate to your application by creating a new dependency in the cargo.toml file. This is the name of the crate, followed by its version number, in our case 0.23.14. Now, running cargo run will fetch and install the image crate. Whilst the image crate is installing, a new function can be created within main.rs named find image from path,
It will take an argument path, which is a string, and we will set the return later. The image crate comes with an I/O module, including a reader struct. We can create a new variable, image reader, set that equal to the reader struct, and this struct implements an open function which takes a path to an image file and returns a result containing a reader. So we can pass in the path as the argument, and we can unwrap the result. This reader can be formatted and decoded to yield the image format, for example a PNG or a JPEG, as well as the image data. A new variable, image format, will be assigned the unwrapped value of the .format method on the reader, the image reader being the variable image reader .format, and we can unwrap the value from within the format. And the variable image can be assigned and unwrapped the value of the decode method on the reader. Now we are interested in both the image and the image format variables, so the two values can be returned in a tuple. So the image as well as the image format can be returned in a tuple. To get an idea of the types we need to return, we can explicitly type our variables. We know this to be a reader, but the reader as a type of a buff reader from a file. The image format is also a type from the image crate, which is image format, and the image another type from the image crate, which is a dynamic image. So we know we need to return a tuple from this function, and in the order it will be a dynamic image. And an image format. Then the necessary imports can be included at the top of the file. That is, importing from the image crate. The reader is in the I/O module, and from the image crate the dynamic image and the image format. You'll most likely get these errors until crate has been installed. Now within the main function, the return tuple can be destructured into two new variables, which we will call image1 and image format1 from find image from path, passing in the image1 field from the Args struct. And the same can be done for image 2. You will notice the error about missing imports for the explicit types within find image from path. The buff reader and file structs need to be imported from the standard library. The buff reader is within the I/O module, and file is within the FS module. There is an error here in the print line statement, but for now we can get rid of that line because we won't be using it. It is important to handle errors which are likely to arise, such as the case where two images of different formats are given as arguments to combine. For example, we'll need some logic where if image1 format is not equal to image2 format, then we'll need to return an error. A semantic way of handling such an error is to return a result. We have encountered some results already, but a result can consist of either an OK or an error variant. What that practically looks like is if we find the formats are not equal to each other, we return an error, normally with a value within. And what this means is our function needs to be typed to return a result, and that result needs to contain some values. But we also need the base case where if there is no error, our function returns OK. It is common to see results return an empty tuple when there is no error. What this means is our result, the type returned on OK, is an empty tuple. Otherwise, it will be some error. The error we will return is an enum, and this is because enums are useful for acting as both types and as values. For now, we can call our error as an image data error, and we will need to define this enum. To do so, we use the enum keyword followed by the name of our enum, as well as the different variants on the enum. We have seen this, for example, with the option enum, which is defined similarly to this, where it takes some with a value, or it just returns none. In our case, we will define one of the variants to be different image formats. As such, we can return within our main function an error of image data errors, the variant, different image formats. I just need to fix this here, image format 1 to image format 2. To make combining the images easier, the largest image is resized to match the smallest image. First, we need to find the smallest image, which we can do using a function called getSmallestImage, or getSmallestDimensions, I should say, because the image will consist of 2 dimensions. Each image will have, in this case, it will be a tuple containing the width as a U32 and the height as a U32. And the second image, we will pass in its dimensions, which will be the same, 2 U32s in a tuple. What we will want to do is return the smallest dimension as a tuple. To compare the sizes, we can declare one variable being the number of pixels in the first dimension, which will be the first dimension, access the first element in that tuple, multiplying by the second element in the same tuple. And we can do the same with the second tuple. Now what we are comparing is the number of pixels in the image. To do this, we will return if the number of pixels in the first image is less than the number of pixels in the second image, then we will return the first image's dimensions, else the second image's dimensions. We will create a function called standardize size, which will take in the first image, which we know to be a dynamic image, as well as the second image, which again is a dynamic image. And it will return both images. We can again return them in a tuple. However, these images will be resized and what we want is, using our getSmallestDimension function, we want to return the smallest width and the smallest height. So we are creating two new variables by destructuring the return of get smallest dimension. Passing in image 1, getting its dimensions by using the dimensions method available on the dynamic image struct, and the same with image 2. Except this is get smallest dimensions. There we go. I think it is helpful if we print out the values of the width and the height, which we can do like so. And we can also add a new line at the end. Now what we want to do is, in order to standardize the size, we will first find out if, for example, image 2's dimensions are equal to the width and the height that we got from calling get smallest dimensions on the image, then we will know that image 2 is the smallest image. And therefore what we will want to do is we will want to resize image 1, and we can use the resize exact method, which is implemented on the dynamic image struct. It mutably borrows the image, and using the width, height and filter type arguments resizes the image. So we can pass in the width that we want, the height that we want, and now we need to pass in a filter type. This type also comes from the image crate, and the type we will be wanting to use is triangle. This is just used for its simplicity, as well as it generally does a very good job of resizing the image without distorting it too much. Now we will need to import triangle. It exists in the image ops, filter type enum, and it is the type triangle. There you go. Now we are wanting to return a tuple with the resized images. So what we can do is, after resizing the first image, we will then also just return image 2 along with it in a tuple. And we will need an else clause, that is, if image 1 is the smaller image, then return a tuple with image 1 unchanged, resizing image 2, passing in the new width we want, the new height, and the filter type. You can see there are errors about using the dimensions method on the dynamic image, and this is because the trait has not been brought into scope, so we can follow the compiler's advice to get the generic image view trait from image, generic image view. And that should be enough to get rid of the errors for now. Fixing the typo in the standardize size function name, we can then, after comparing the formats, declare image 1 and image 2 again, this time destructured from the standardize size function, having resized whichever image is the largest. Now, it is all well and fine that we are handling resizing the images. However, we know that the end goal is to create a new image using the pixels from the two input images. So to handle the output, a temporary struct can be created to hold the metadata for the output image. And we can call this struct FloatingImage. And the metadata we will want is the width as a U32, the height as a U32. It will contain some data, being the pixel values, as a Vec of U8s, because the pixel values will exist between 0 and 255, a U8 perfectly fits that number type. We also want the name of the image as a string. In order to create this floating image, we can do as we did previously with the Args struct, and we can implement the new function, which will take in a width and a height, as well as the name, and it will return a new floating image. And what this will look like is a floating image with a value of the input width and height. We know that there will be some sort of data, as well as the name. Now for the data, when we create the new floating image, we won't have the pixel values yet, but we will need to reserve the space for them in memory. In order to do this, we can declare a buffer, and that buffer could be a fixed value, such as, let's say, buffer capacity. Set this to some number, for example 3,655,744, and then the buffer itself will be a vector with the capacity of that buffer capacity. And then we can assign the buffer to this data. An interesting thing about Rust is that you can use this number format to make your numbers easier to read, where you separate 3 digits of your number using an underscore. However, what we have here assumes that any image we input will not be larger than essentially this number of bytes. However, we can more dynamically size this based on the fact that we know that our image will consist of a height. We can multiply that by the width, and to get the number of pixels, we multiply this by 4. The reason for this will be clearer as we go through this next, where we will be using RGBA values. So we are multiplying by 4 because we are using the red, the green, the blue, and the alpha values for each pixel. You'll see we have a warning here that there are mismatched types with capacity function expected to use size but found a U32. The reason buffer capacity is of type U32 is because we used the height and the width to create it, which are U32s. Normally, Rust would automatically convert or try to convert the number type into the correct type. However, in this case, we cannot be certain that this is possible. So, we can follow the advice the compiler is giving to try to convert the value. Otherwise, if that's not possible, fail, or in this case, panic. So we can TryInto and then unwrap. However, in order to use the TryInto method, we need to bring it into scope, and it exists in the standard library in the convert module of the TryInto implementation. So we can just bring that into scope. Now within main, we can create an output variable containing the new floating image. We will use image 1's width and image 1's height as the inputs for the new function. We could use image 2 as well, but considering image 1 and image 2 have been resized to be the same size, their width and height will be identical anyway. And we will want to pass in the output field from the Args struct, as this will be the name of the function. and the location which we will later use. At this point we can deal with the error that we have up here, which is saying that the trait debug is not implemented for image data errors. We can resolve this by following compiler's advice to use the attribute and derive the debug trait for our image data errors enum. The reason this is necessary is because main returns to the standard output the result of running the code, normally either being a status of 1 or 0. And in order to return to the standard output, the debug trait needs to be derived. From here, we can run our code to see if everything is working as expected. What we will need are 2 images as inputs. To get these images, I will just be importing them into our combiner project. Within the images folder, we have 3 images here. First being my profile picture, the other being the freeCodeCamp logo, and the other an inverted freeCodeCamp logo that we might use later. Then, in order to test our code, we can go cargo run, passing in the arguments which we know to be images folder. We can pass in my profile image as well as the image to the freeCodeCamp glyph. Both of these images are PNGs. We also need to specify an output location, which we can say is within images, and we can set it to test.png. We have not currently implemented anything for the output image to go into, however we still need to provide the argument. We get a few warnings. The code panicked because I called the wrong folder name here. Running again, we can see that the width and the height are output, and so everything is working as expected. As I said earlier, in order to process the images, they are converted into a vector of RGBA pixels, and the pixels are stored as U8s because their values are between 0 and 255. So, in order to process our images, we'll be creating a new function called Combine Images. And this will take in image 1, which we know to be our dynamic image. Image 2, the same. And this will return our Vec of U8s. The dynamic image struct implements the toRGBA8 method, which returns an image buffer containing a Vec of U8s, and the image buffer implements the intoVec method, which returns the Vec itself. So, to visualize that a bit better, let's declare a new variable called Vec1, which will be image1. We will call the toRGBA8 method on the dynamic image. You'll notice that it returns an image buffer containing an RGBA U8 as well as the Vec of U8s. So in order to get the Vecs out, we can call the intoVec method on the image buffer. Likewise, we can do for Vec2 and image2. In processing our images, we will want to alternate the pixels of the 2 images. So what we'll do is we will create a function called alternate pixels. And what this will do, it will take in the 2 vectors, and it will return our Vec of U8s for us. So let's define that function. We know that it takes in 2 Vec of U8s and it also returns a Vec of U8. First, we need to declare a variable, which I will call combine data, that will hold the data of the two images after they have been alternated. In essence, we'll be pushing the pixels from one vector and then pushing the pixels from the next vector. And in order to size the combined data, we will match it using a Vec macro. We want U8s, and we want the number of U8s to be the same length as any of the vectors passed in. In this case they're the same, but we will just set them to be the size of the first vector. What this Vec macro does, it will create, for example, if vec1.len is equal to 100, or no, let's say 5, then the Vec macro will create a vector of U8s of that same length. Now, what else we will do is we will use a while loop to go over each pixel. In this case, we will refer to the pixels as indices within the length of the vector. And first we will need to declare this I variable. And we will know that we'll want to mutate the I variable, so we'll declare it as a mutable variable, starting at 0. And within the while loop, we will increment by 4. This is done because we are using RGBA sets within the vector, and being 4 values, we need to increment I by 4 as we're accessing the indices within the vector. Using the modulo operator, we can say that if I modulo 8 is equal to 0, we will splice into combined data the RGBA set from Vec1. In order to do this, we need to set the range. In our case, the range will be from I until I plus 3, and we will need to get the RGBA set from the first vector. To do this, we will create a little function, set RGBA. What this will do, it will take in the first vector, it will take in a starting index as well as an ending index, and it will return the RGBA set from those indices. Otherwise, we will want to do similarly this time. Passing in Vec2. So, let's define that set RGBA function. We know that it takes in a vector. This vec will be a vec of U8s. It will have a starting index, which is a usize, as well as an end index, also a usize. And we will want to return the vec U8 set. In order to do this, we will be declaring a mutable vector, RGBA. It's just a new vector. And for every index in the start until the end inclusive, we will declare a new variable val. We will set this equal to vec.get and pass in the index that we are interested in. Then, after doing that, we will push that index to the RGBA vector. We will push that value, and then we will want to return that vector. We have initially here where get returns an option. What we could do is just unwrap to get the value. However, there is a chance that that value doesn't exist. So what would actually be better is for us to match on get call, and if there is some value, let's call that value D. What we want to do is return the value, and if there is none, what we want to do is potentially panic and say that the index is out of bounds. Now, you will notice that we get an error up here saying that the function expected to return a vec of U8s, but instead is returning an empty tuple. To resolve that, we can return the combined data. You'll notice we have an issue here where combined data is being spliced, so what we actually need to do is declare it as mutable. And we get an error down here saying that the function is expected to return a vec of U8s. However, it is actually returning a vec of U8s, but the U8s are referenced. What this means is we are pushing referenced values. In this case, currently val is equal to a reference of U8. What we want is for it to be just a U8. In order to do that, we can use the asterisk before the variable. What this does is dereference the value. That resolves the error. However, now we have a new error saying that the borrower of a moved value vec1, where the value borrowed after being moved. Here we can see that vec1 has been moved. Why this is because within the while loop, we are passing vec1 into the setRGBA function. We don't actually want to pass in the whole value. What we want to do is we want to pass in a reference to a value, a pointer. And the same needs to be done with vec2. Now we need to adjust the function definition, as it's not accepting a vec U8, it's accepting a reference to a vec of U8s. To clarify, the syntax here is Rust's range syntax, which allows the range to be inclusive of the end value. So far we haven't called these functions yet. However, what we need to do first is to set the data of bind data into the output image, which we actually need to call output. A method on FloatingImage needs to be defined to set the data field of the output to the value of that combined data, because currently what we have for the data field is just a buffer, not the actual pixel values we are interested in. So far, you have only defined functions on structs. However, now we are wanting to define a method. Methods are defined in a similar way, but they take an instance of the struct as their first argument. You saw this with the next method. So we are going to define a method called setData on the floating image. What this will do is it will take a mutable reference to self, as well as the data we are wanting to set, which is a vec of U8s. What this will do is return a result. Either on OK it will return an empty tuple, or it will return one of our image data error enum variants. What we can do is first make sure that data.len is greater than the current floating image's capacity if the length of the data is more than the capacity of the current floating image. What this means is we cannot store, we did not reserve enough buffer in order to store that data. So here we will return an error, and this type of error will be an image data errors, and we'll need to declare a new variant, and this will be buffer too small. So we need to define that variant to buffer too small. Otherwise, we can just set the data to the data that is passed into the method. In that case, the result is OK. Now within main, we can call that method on output. Passing in the combined data. You'll notice that again only one argument is passed into setData, because implicitly the first argument of a method is self. we need to define combine data. Let's do that first and say let combine data equal to, we have the combine images function, and it takes in image 1 and image 2. And what we've done is we've made it that set data returns a result. An interesting thing you can do with Rust is propagate that result value by adding a question mark at the end of the expression. What this will do is essentially unwrap the value, but it propagates it into the current function, and as main already returns a result of either OK with an empty tuple or an error with image data errors, which is the same function signature as set data, we can use the error propagation operator. Finally, the new image needs to be saved to a file. The image crate has a save buffer with format function, which works like this. We can use save buffer with format. We need to pass in the path of where we want to save the image, which we have stored in the name field of output. We need to pass in the data from output. However, this needs to be a reference to the data and not pass in the value itself. We need to pass in the width of the new image and the height of the image. We need to define the color type of the image, where we can get the color type from the image crate, and we know that the type is RGBA and they are U8s. And finally, the format of the image, which will be the same as image1 format. This function also returns a result, so we can unwrap that, and I need to remember to correctly name my variables. You'll see we still get an error about output, where we cannot borrow it as mutable because it's not declared as mutable. This is because in set data, as a method, it takes a mutable reference to self, which in this case is output, so we need to declare our output variable as being mutable. To test out our image combiner, we can once again call cargo run and pass in the arguments, which we know to be images, to my profile PNG, images to the FCC glyph, and we'll output this image into the images folder, and we will call it output.png. Running this will compile the code, and once it has finished, we should be able to navigate into that images folder and find the output. And there it is, the profile image and the freeCodeCamp glyph combined into one image. Although the application is finished, we have a lot of calls to unwrap within our code. What this means is, if at any point there is an error during runtime, our code will panic, and it may not provide the best user experience or the best error to help a developer debug as they are using the application. So one thing we can do to extend this, as we already have some basic error handling within our main function, where we are returning a result where if there are any errors, we are returning image data errors, which is our enum. We can extend this further with some more common types of error. So, for example, fixing up the find image from path function, instead of unwrapping on the reader, open returns a result. So what we can do is we can match on the result and if this expression is okay, we will get the image reader. Otherwise, if there is an error, we can get this error out in a variable named e, and then we can return an image data error. And we will add a new type of unable to read image from path as a variant on our image data errors enum. And we can pass an e as a value to the enum. So let us define this new variant. We named it unable to read image from path, and we know it takes in some sort of error. Now, this error exists in the standard library as standard.io error. Next, we need to move our logic within this match arm, but we can continue with the next unwrap statement. However, format returns an option, and the general rule of thumb I follow with how to handle options versus results is, as we have already done with a result, we match on the result and we handle the OK variant versus the error variant. However, if we are dealing with an option, what I like to do is use an if-let statement, and that looks something like this. If let there is a value, that is, the option returns sum, then we can declare a new variable called image format. And if this is the case, we can perform some logic. Else, we can return an error. In this case, we'll need to explicitly return error image data errors, and we will declare a new variant called unable to format image. And something we can do here is pass in the path. That way our error has more information with it as to which image it failed to read. Now, we cannot pass in path as is because we are moving it into this open call. So what we need to do is pass in a reference to the path to the first open call, and then we can define that variant. And we call that variable unable to format image, and it took in a string. Then, handling the image logic, as decode returns a result, we can match on the result. Match on the result, and in the arms, if OK, we can get the value in a variable called image, and we can return OK with the tuple that we expect being image as well as the image format. Otherwise, if there is an error, we can get the error in a variable called e and return that error in, again, another variant of image data errors, enum. And this variant we will call unable to decode image. And we will pass in that error as is. So to declare this new variant, which we named unable to decode image, it takes in a specific error from the image crate, which is called image error. As such, we need to add it to our dependency. Then we can remove some of this logic that we are no longer using, and we need to fix up some things. So we need to define our function to return a result, and on this result it is either returning the tuple which we originally had, otherwise we know it is returning one of the image data errors variants. Then, as we learned earlier, we can propagate the errors into the main function, as we are calling it, using the error propagation operator. And finally, we have one more unwrap to deal with, and this is on the save buffer with format function. Now what we can do with this is, as it is returning a result, however we are only actually interested in the case where there is an error, we will again use an if-let expression, destructuring the error from the call. This way, we can just return the error if there is one in a new variant called unable to save image and pass in that error. Otherwise, we can return OK to define that variant, which we named unable to save image, and we are passing in again an image error from the image crate. We have also rejigged this to no longer be using these imports. So what we can do is just remove that. And just like that, we are handling our errors in a much better way to inform both the developer and or the final user of what is happening when any of these errors arise.